Hello, this week we're going to be talking about uncertainty in games, two different chapters in the book and seemingly two different topics. But I'm going to weave them together by showing how we need to embrace uncertainty and how games is one way to do that. We're going to look at two approaches and several concepts. The first set of concepts we're going to look at is uncertainty and ignorance, and the sources of those uncertainty, and how, and in this particular course, we're going to focus on that, how that relates to resource use. And we're going to combine that by looking how we can take a games approach. And a games approach is simply where you make some choices and an opponent makes some choices, and you really don't know what choice they're going to make. So that's where the uncertainty comes from. And then we're going to combine these two approaches, that is, looking at environmental problems for what we know and what we don't know about them, and then looking at environmental problems for how we might make decisions about them, our decisions versus some opponent's decisions, or decisions or outcomes that are determined by nature. So first of all, uncertainty. Let's look at three related concepts. Risk, which is something you can calculate, and because you can calculate the risk, you can deal with it probabilistically, and you can take actions to reduce the risk by avoiding factors that increase or increase that probability. Uncertainty is where you really don't know what's going to happen because there's too many possible outcomes. It's a complex system. You just don't know, and therefore, you just can't calculate any risk. We're going to talk about that in a second. And indeterminacy is a term we're going to use here when, as humans, we create some new thing, and by using a lot of energy or effort, we've created such a whole new system that it takes on a life of its own, and then that's a sort of particular type of uncertainty. And again, I'm going to describe that a little bit more, and it's described in the book. Okay, now one other thing is uncertainty doesn't go away. We can't just turn uncertainty into risk. Again, I'm going to explain why that is later. And in wicked problems, the uncertainty, or what we don't know, is really a key component. And that's because of the components of uncertainty all add into what people are going to do, how their values are going to change or not change, what decisions they're going to make, how well we define the problem, and then as we learn more about the problem, we change the knowledge base for that problem, and that changes people's values. So it's an interaction, a complex interaction between values and knowledge that makes wicked problems wicked. Okay, so the sources of uncertainty, if we were just looking at a particular scientific problem, would be the inherent unpredictability of the system itself. Say we're studying a lake, there's just some behaviors of that lake we're not going to be able to predict. And then there's a limit to the perception and measurement, and that's more on the scientific end. What's the limit to our technology? What's the limit to the amount of money we can spend employing technology? And also, what if we employed so many research boats out in a lake that it actually changed the nature of the lake? So there's a limit to how much we can, how much effort we can put into studying a system and have it remain the same. And then human volition, and so this is an environmental problems. There's always human values and human decisions in there. We just don't know what decisions people are going to make about the lake or make upstream in the watershed or even in the economic regions surrounding the lake. We have a hard time predicting that, so that ends up being a source of uncertainty in environmental problems. So from those features, you can see that uncertainty is really a dominant feature of issues we have to deal with. So let's just break that down. We have information. One of the, I'm going to give you an example, say for global carbon fluxes. For information, we just can't set up rigorous controls for large experiments, especially if we're talking about global carbon cycles. We only have one globe. We can't, one Earth. We can't just set up replicates. We have limited money to devote to studying large problems such as this. And then, so just the example of trying to measure some of these important global carbon fluxes that you saw in the readings from last week, it's just very difficult to pin those down. They could be off by a factor of 10 very easily, which would make a big difference in how we interpret the models. Another is just this idea of natural variations and technical issues, and we just have limited ways to measure some of these important processes. And CO2 fluxes is a good example. How do you measure the carbon dioxide flux going from the ocean into the atmosphere? It changes every day because of the weather patterns. It changes whether it's raining or whether there's net evaporation. All of those multiple factors in just seasonal weather make a big difference. And then measuring, what's the appropriate area to measure it over. All of those are there's technical problems that limit our ability to pin this thing down. And then finally, humans make decisions in that same realm about carbon flux. And for example, it'll have a big impact on carbon flux and where the carbon goes and how it's handled if countries adopt a carbon tax. But that's just so much up in the air all around. It's very difficult to predict what might be the impact of that carbon tax. And then it's even more difficult to predict whether people are actually going to enact it in different countries or not. It's an important concept in this class that uncertainty is different than risk. And you might hear these terms be used interchangeably in other contexts. We're going to use them differently. So you can calculate risk, and one way to mitigate risk is to decrease your risk factors or find a way to cover those risk factors. So insurance is a good example. When there's well-known risks, you pay more or less insurance depending on your risk factors. So that's a way to mitigate the loss you might get from your house burning down or flood or something like that. The modes for dealing with risk and uncertainty are also very different. In risk, if we're going to approach an environmental problem that included a lot of risk analysis, we might use a portfolio approach of different methods. Each has its strengths and weaknesses, and balance how much we invest in one part of one attempt or one type of solution as being the most promising, put the most money in there, but then also maybe put some money into some long shots that would cover some of the risk in case the system behaves a little differently than we thought was the most probable. This is included in sophisticated project management. It includes risk assessment, and it deals with these issues just as a matter of course. For uncertainty, we take a different approach. So for example, if we wanted to talk about something doing with the forest, we might generate broad scenarios of the future of how people are going to deal with the forest resources, probably based on something like world views or economic outcomes. We generate these scenarios, and then we don't really know which scenario is going to come to pass as the real future, but we look at what happens in each one of these scenarios. We're going to talk about that later in the course. And scientific adaptive management is another approach we would take, and it's one of the tenets of scientific adaptive management that any manipulation you make to try to solve a problem will also decrease the uncertainty for people following you that are also addressing that same problem. So it's built in. Scientific adaptive management is not just trial and error, but it's a way to design the experiments and the manipulations so they decrease uncertainty. Okay, now I just want to leave you with this. We want to deal with uncertainty in a positive manner. And the way we do this is if we identify this is uncertain, we're ignorant about these particular aspects, that's good. We can, by clearing up that assumption, this will help. We can, one thing, you don't want to underestimate the uncertainty. A lot of problems have gotten even bigger because people underestimated, they thought they knew stuff they didn't. Because then we can have tools to deal with it, such as using scenarios, using entrepreneurism, using scientific adaptive management. And then we need to develop ways to communicate and talk about this. And this is between people in the scientific community, people in the governance community, people in industry, and the general public who are active in trying to solve these problems. Okay, now one way we can talk about uncertainty is the games approach. And the games approach is really a decision support framework, and you make a decision, and then your opponent, or nature, as we'll see in a second, has some unpredictable input. So we start with a decision square such as this. You have your choice of two options, your two actions, and your opponent has two actions, and you get these different outcomes depending on what you choose to do and what your opponent chooses to do. So here's an example of a natural resource problem that you might face with your neighbor. You share the same well, and you're using a lot of water, and you might run dry. So you decide whether you're going to pump heavily from the well or conserve water. Your neighbor does the same thing, has the same choice. You don't really know what he's doing. You don't have a gauge on his, and you can't really force him to do whatever he says he's going to do. He could just change his mind. So if you both pump heavily, and the well goes dry in the middle of the season, maybe you're growing crops with it, you could both lose crops and lose lots of dollars that you invested into it. So this is really the worst possible outcome. Again, if you pump heavily but your neighbor conserves, you probably do pretty well, except for the cost of pumping. You might make more money. And conversely, if you conserve water, maybe you're not going to make as much money on crops, and your neighbor's going to make a lot of money on crops. And if you both conserve, you both make less money, but the well doesn't go dry, so you don't have that expense to have to deal with. So depending on the relative amounts of money that you would gain or lose in these scenarios would tell you, what's a good solution. But it's right on the face of it that you really don't want the well to go dry, and so the precautionary principle would be try to stay away from any situation that would leave the worst possible outcome, and that would be for you both conserve water. But when you hear things about the tragedy of the commons and the prisoner's dilemma, there's a different sort of stable solution, which is you both go for whatever you can get out of the system. Okay, so we're gonna a little bit in the reading and then in the videos and they're going to address this idea that you could look at the tragedy of the commons as a games view. And by doing this is the tragedy of the commons. It was a landmark paper written by Garrett Hardin. And one thing, it's going to daylight the assumptions that are built into this the tragedy of the commons conclusion. And we're going to look at the issue of with the commons, whether you graze or whether you don't graze, that's the decision. And then how communities communicate and cooperate, as how they form institutions to deal with that. And again, that's a major assumption that Garrett Hardin got incorrect, was that local communities actually do deal with these issues of common resources very well. Okay, another thing I wanted to bring up here, because it underlies a lot of the discussion about using natural resources, is this sigmoidal growth response, and sometimes it's called the logistic growth model when you're using a very particular mathematical formula underneath. But the sigmoidal growth is generally looks like this. At low population, in the beginning there's lots of resources, and the population is growing relatively fast. The slope is low at A because there's not very much population, but the actual inherent growth rate there is at the fastest. Then as it goes through B, it goes from an inflection point from going from a positive feedback to a negative feedback, and in the region of C it's slowing down. By the time it gets to D, it's at a steady state where the population is either stopped growing, which is one form of steady state, nothing in, nothing out, or it might be in a steady state between births and deaths. And this underlying model is very important because a lot of the discussions that you're going to see are about growth rates and maximum sustainable yield and the carrying capacity. Okay, that was a little detour, and now I'm going to go back and just go back to the games approach as if you're playing a game against nature, where nature throws at you some uncertain outcomes. And here's a good example. It's in the chapter. I'm not going to dwell on it too much, but you have several choices in preparing for potential storms. You could invest in preparing for a storm, heavier windows, better roofing, that sort of thing. Or you could just hope it doesn't hit you and take that money and do something else with it. Well, then the storm either hits or it doesn't, and that's the uncertainty, and that's how you don't know if like a tornado is going to hit your house exactly, or whether a hurricane is going to hit your community exactly. So there's very uncertain about the level of damage your particular house is going to take, and yet you're the one that has to make that decision. So that's how we combine in games approach and this uncertainty. Okay, now summary. Moving forward, uncertainty is involved in all environmental issues. It's because we have limited knowledge, and in fact we are less than limited knowledge. We're really fantastically ignorant about most systems we're trying to manage. And then the other thing is, as we change natural systems, we actually generate more uncertainty. We inject CFCs into the atmosphere. We bulldoze a wetland, and we try to replace it with something. We're actually creating more uncertainty than we're removing in that case. So the games approach is just one way to make a positive step toward that and try to pin down what we know and what we don't know, and what possible outcomes we might see. And other ways are to engage in the problems with identify possible range of outcomes, that's scenario approach, or devise a scientific process to reduce uncertainty, and that's scientific adaptive management. But I want to leave you with a caveat, which is that it's actually very difficult to deal with uncertainty in public discussions. And here's really sort of the reasons why. People trust ideas and solutions that they're comfortable with, that they've seen before, seen components of it. They're not comfortable at all with uncertainty, because that, just by the definition of it, is something they don't know. So as we move towards sustainable use of resources, we often need trust networks in order to build out these solutions. And that means we're going to leave some resources on the table that we're not going to use, where we trust that no one else is going to use them either, like the common pool resource or grazing on the commons. We need to be able to leave that there and not have somebody just steal it. So even though it's nice to say that environmental science needs to embrace uncertainty, it doesn't mean the public will. So it comes down to that some of these solutions that we're preparing, they might have to contain some pieces that people recognize and that they trust, but then as we build them out into more sustainable solutions, they're actually, the innovation is really putting together old pieces in new ways.